Hi everybody, Dr. A here, and in this video we are going to be exploring another example of two-dimensional rigid body equilibrium in solving for external support reactions. So let's take a look at the system we have. We have a beam that is supported by a pin connection at B. We notice a little triangle here. And it's also supported at point C by a weightless link. We see that written over here. This is a weightless link that is labeled CD, okay? And that weightless link is at a 50-degree angle. Now, the applied loads here include a 3 kilonewton meter moment applied at point A, and then between B and C, we have a linearly varying distributed load. This is like a trapezoidal distributed load. At point B, it has an intensity of 25 kilonewtons per meter, and at point C, it has an intensity of 10 kilonewtons per meter, and we also have some given dimension lines shown here. So even though the directions say solve for external support reactions, you always want to get started with drawing a free body diagram of the system. So we're going to draw a free body diagram in which we show all of the known and unknown forces and moments acting on the system. So we know we've got the 3 kilonewton meters applied here. At the support reaction B, that's a pin, so we're going to have a By force that's developed and a Bx force that's developed. And then over at C, we're going to have an axial load developed in the weightless link in the direction of the link, along the longitudinal axis of the link, and we're going to call that FCD. Now, we need to draw the other knowns. So we know that we have this trapezoidal load acting from B to C, and at point B, it has an intensity of 25 kilonewtons per meter, and at C, it has an intensity of 10 kilonewtons per meter. And then over at C, where that weightless link is located, we're going to show on here that 50-degree angle that FCD is making with a horizontal. And we also need to show all of the appropriate dimension lines. So here we have a 2-meter dimension line and a 4-meter dimension line. So this is our free body diagram. It looks a lot like the original figure, except we're showing very clearly the unknown support reaction forces in the system. Now remember, we know that we have 3 external support reactions, Bx, By, and FCD. We know the orientation of them, but we don't know the direction that they're pointing. So we assumed Bx is pointing to the right. We know it's horizontal, but we're assuming it's pointing to the right. We know By is vertical, but we're assuming it's pointing up. And we know the force in CD is along the longitudinal axis of where the link is, but we're assuming it's pointing away from point C. That's actually assuming a tensile effect. So now that we've drawn the free body diagram, we're ready to apply our equilibrium equations. Let's start with summing moments. So as we've mentioned before in previous videos, and as you know from maybe previous classes, you can sum moments about pretty much any point. You just want to pick a point that is convenient, that'll make your calculations a little less tedious. So what I did was I said, let's sum moments about point B, and we take counterclockwise as positive. So looking at this free body diagram, we're going to sum up all the moments that generate a tendency of rotation about point B here. So moving from left to right, we're going to have the positive 3 kilonewton meters. This is an applied moment, so it is going to show up in that moment equilibrium equation. Bx and By do not show up in this equilibrium equation because we are summing moments about point B, and Bx and By are at point B, thus they do not generate a tendency of rotation. The next thing that tries to rotate the system about point B is this trapezoidal load. Now, when you're dealing with a trapezoidal load, my suggestion is break it into simple shapes. I would break this into a rectangular segment and a triangular segment. And I would have a rectangular force, you can call it P sub r for rectangle. And I am also going to have an equivalent triangular force, which you can call P sub t for triangular force, okay? So let's look at the rectangular force first. How are we going to form that? Well, the rectangular force comes from the intensity of the rectangular component of this load multiplied by the length over which it is distributed, okay? So that intensity is going to be 10 kilonewtons per meter, okay? So we separated this such that the rectangular portion, the intensity of that is the 10 kilonewtons per meter. So we're going to say minus 10 kilonewtons per meter times 4 meters, and then its perpendicular distance away from point B is half of that 4 meters, which is 2 meters, as I just drew here. So we're going to say times 2 meters. Now, what about the triangular portion? We can't just ignore that. We have this triangular slice right here. The area of this triangular slice is given by 1/2 base times height. So we're going to say minus 1/2 times 15 kilonewtons per meter times 4 meters. Now you may be wondering, where does the 15 come from? Well, remember, we're looking at this triangular segment, okay? What is the height of this triangle? The height of just the triangular portion is 15, because the 25 is the total height of that trapezoid, where the bottom portion coming from the rectangular slice is the 10. So you say 25 minus 10, and you leave this 15 kilonewton per meter height here, okay? And then times 1/2 times 4 meters gives you the area of the triangle. Now you also need to multiply by its perpendicular distance away from B, which comes from the centroid of a triangle, which, if you remember, is 1/3 of the dimension from the back face. So it's going to be 4 meters over 3. So we're going to say this is times 4 meters over 3, okay? The next thing that's going to generate a moment is FCD. FCD is generating a moment about point B, and specifically the vertical component of FCD is going to generate a moment about B. See, the horizontal component, while it is there, it's along the line of action of point B, so it's not going to cause a rotation about point B, but the vertical component will. And in fact, that's going to cause a counterclockwise rotation. So we're going to say plus FCD times the sine of 50 degrees times 4 meters, all equals 0. And we can do some rearranging and solve for FCD and get a positive 38.18 kilonewtons. And the positive means that FCD is pointing in the direction that we assumed in the free body diagram, which is up and to the right. And that's why I put that up to the right vector symbol near my answer. So that's part of my answer. Next, I can apply my next equilibrium equation. I'm going to say sum of the forces in the x direction equals 0. Now, for this equilibrium equation, you're going to look at everything that has an x component moving from left to right, and specifically every force that has an x component. So the first one we encounter is Bx, and then the second one we encounter is FCD that we just solved for. So we're going to say plus FCD times the cosine of 50 degrees equals 0. Well, you know FCD. We just solved for it. So you substitute this value of FCD into your equilibrium equation for x forces, and we'll do some rearranging, and we'll get Bx equals negative 24.54 kilonewtons. Now, what does that negative mean? That negative means that your Bx is actually pointing in the opposite direction of what we assumed in the free body diagram, which in this case is pointing to the left. Now, last, we're going to use Our third equilibrium equation, sum of the forces in the y direction equals 0. We call things pointing upwards positive. And looking at this free body diagram, we want to include every force that has a vertical or a y component, starting with By. So we're going to say By minus, and we're going to look at the rectangular component again of that distributed load. That was 10 kilonewtons per meter, and that's distributed over a 4-meter length. And then we're going to minus the triangular portion. Now the area of that triangular slice is 1/2 base times height, which is 1/2 15 kilonewtons per meter times 4 meters. Notice this is force equilibrium at this stage, so no moment arm, just finding the forces. We also have the vertical component of FCD, and that is pointing upwards in the free body diagram. So that will give us a plus 38.18 kilonewtons times the sine of 50 degrees. And all that equals 0. And so we can do some rearranging, and we'll get By equals 40.75 kilonewtons, and that's positive, which means it is pointing upwards as we had assumed in our free body diagram. So in summary, we are going to write down Bx equals 24.54 kilonewtons pointing to the left. By is 40.75 kilonewtons pointing up, and FCD is 38.18 kilonewtons pointing into a quadrant 1 direction. And that will conclude this example. Hopefully you wrote all of this down. If not, rewind, watch it again, and write down everything. Remember, this is not a spectator sport. You got to write it down so you can learn it. All right, please hit like and subscribe, and we'll see you in our next video.